Hi trig students, this is section 9.2. It's called Polar Equations and Graphs. So remember, this blank packet is located under content, and we're going to have 6 sections total in this chapter. We're going to have 5 from chapter 9, 9.1 through 9.5, and then we're also going to have section 10.7 that's going to be added on. So a total of 6 sections. So this packet is a little long. It's longer than our previous packets. The first few pages, though, all we're doing is really talking about specific shapes. And then we don't jump into examples until about halfway through. So this first part is just going to be us playing around with your calculator and getting you familiar with 5 polar shapes that we are going to use. So you're definitely going to need your graphing calculator, and let's jump right in. So polar equations are equations where r and theta are the variables. So no more x's and y's, these are the variables now. The simplest equation for many types of curves are polar equations. So we're going to look at 5 types. Now, I'm not interested in you plotting these by hand. I really just want you to be able to put them in your calculator, okay? So anytime it asks you to graph them, it's in your calculator, and it's really just to identify the general shape. So let's figure out how to do this. So in your calculator, 2 things you're going to have to do, and here they are. These are important. You're going to go to mode. Now, the second one says radian mode instead of degree. That's easy enough. We always want to be in radians for polar mode. But this first one you may not be familiar with. The first one says to make sure your calculator is in polar mode, P-O-L. So right below radian, you're going to see a line that says function, parametric, polar, and it continues on. Function, this F-U-N-C, this is what we use anytime we're dealing with x's and y's. So that's why it's always been in that mode for you. But now for this section, we're going to scoot over to the POL mode and hit enter. That is so important. If you are not in polar and radian under mode, you are not going to be able to graph these. So we want both of those, and then we're going to quit. Okay? All right. So let's set this aside for now. We are going to graph both of these examples in our graphing calculator, but let's talk about them for a minute. So our first type of graph that we're going to look at is a circle. Now, I know you have seen circles your whole life. Okay? Well, circles, the equation in algebra for a circle is pretty complicated if you remember. It has an x squared term, a y squared term. Depending on the form of the equation, you may have other x and y terms. It can be a lengthy equation. In polar form, circles are really simple. So you have 2 types. You have this type where r equals 2a cosine theta, and this type, r equals 2a sine theta, okay? When cosine's involved, and that's the only difference in these two is cosine and sine, when cosine's involved, you have x-axis symmetry. So remember, we could fold this over the x-axis. Your center of your circle is going to be a 0, and the radius of your circle is a. Okay, so if this is our equation, and we're going to graph it so that you can take a peek at it, but what I know is that I'm going to have x-axis symmetry because there's a cosine. I also know if I pull out a 2 out of this 4, then whatever is left, in this case it also happens to be a 2, is going to be a. So if a is 2, that means I have a circle here whose center should be at 2, 0. Okay, that should be my center. I also notice that I am going to have a radius for this circle of 2 because that's my A. So if I come out in all directions 2 units off of this center, I'm going to be looking at a circle that looks like that. Okay, let's see if that is true for this particular equation. Okay, so what I'm going to do is go to y equals. Well, now this is very different. I used to have y's here, but now that I'm in polar mode, I have r's. Okay, so I'm going to put in 4 cosine, here it is, and then here's where it gets interesting. Remember, this button used to be for x. Well, now we're in polar mode. When you hit this button, you're going to get a theta. There it is. So here we go, r equals 4 cosine theta. I'm going to hit zoom standard because I'm not sure what my last window was. And look at there. Now, this looks a little bit more like an oval or a football simply because of the way the calculator screen is. But it's supposed to be a circle. And if you notice, there's our center. It does have the x-axis symmetry, and it resembles exactly what we thought it would as far as the placement goes with the radius in the center. So that is how you graph a polar equation. Okay, let's try this next one. Now, the only difference here is that we have a sign, which means we're going to have y-axis symmetry for this guy. Our center is not going to be A0, it's going to be 0A, but our radius is still the same, A. So here's an example. Okay, so I know I'm going to have y-axis symmetry because of the sign. I'm going to pull a 2 out of this coefficient. That leaves me with a 1. That means A is 1. Okay, because remember, I have to pull a 2 out to see what A is. All right, so knowing that my center, it's not going to be 1, 0. It's going to be 0, 1. That's because of sign. That's because we have y-axis symmetry now. But my radius is going to be 1. So my center is now going to be up here. I'm going to have a radius of 1. So I'm going to go out in all directions 1. And there it is. That's going to be my circle. It's a little wobbly there, but there it is. Okay, let's try it. So I'm going to go back to y equals, clear it. I'm going to put in 2 sine. Remember, here's my theta. R is already over here on the side. Got to solve for R for these guys. Okay, and I'm going to graph him. There he is. He's kind of small, but there he is, sitting right up top, just like our picture that we drew. Okay, right there with the y-axis symmetry. Okay, easy enough. All right, let's look into 2 more examples where circles are concerned. Okay. Now, this bottom one, let's skip him for just a minute up here and go down here to the bottom one. This bottom one down here, all we want to do is be able to identify the center and the radius and a little picture, a little graph of him, right? It doesn't have to be exact, just a little graph. Okay, well, I know this is a circle because he is of the form r equals 2a sine theta. That's my circle form. I know I'm going to have y-axis symmetry because of the sign. If I pull out a 2, I'm able to find my A equals 3, which means that I have a radius equal to 3. And my center, because it's y-axis symmetry, needs to be on the y-axis. So it's going to be 0, 3. So what I'm looking at here is 1, 2, 3. There's my center. I'm going to have a radius of 3, so I'm going to go out 3 in all directions here. The best you can. Just draw a nice little picture, and there he is. Okay, that's what we predict he will be. Now, we're gonna just make sure that is what happens, okay? So I'm going to go back to my calculator. I cleared it out. I'm going to put in 6 sine theta, graph it. Sure enough, there he is. There is our circle, just like the circle we drew. And again, even though he's sort of footballish, that's just the way that a calculator draws those sometimes. So that's exactly what we have. All right, so why did I skip this guy up here? That's because he's a little different. He does not have sine or cosine involved in him. So he's actually not, he is a circle, but he does not have x-axis or y-axis symmetry. He is going to have origin symmetry. And his center is going to be 0, 0. His radius is going to be 5. So this is a funny little circle. He does not have sine or cosine involved, but anytime you just simply see r equals a number, you are dealing with a circle whose center is at the origin, and whatever this number is that r equals, that is your radius. So if here's my center, and if I were to go out 5 in every direction, okay, that's a big circle, but if I were to go out 5 in every direction, oh, that's gonna look terrible. Okay, there you go. Well, he's supposed to have been 5 in every direction. There is supposed to be a beautiful little circle there. Okay, let's look at that on our calculator. Here we go, we're gonna clear out that. So all I'm gonna need to put in here now is a 5, r equals 5. I graph it, that's supposed to be our circle. Right there, that bothers me. And there we go. Okay, again, even though it's a football, it's supposed to be a nice circle at the origin. All right, now, I'm also gonna throw in a My Math Lab question at this point. This is a My Math Lab question. Okay, My Math Lab, I think it's like question 2 or 3. Okay, so 2 or 3, I don't know. Just kind of keep it in mind, okay? My Math Lab wants you to take this r equals 5 and transform this polar equation to a rectangular equation, and then be able to identify all of these items from the rectangular equation. So remember, a polar equation is one that only contains r and theta. A rectangular equation only contains x and y. So those are my rules that I have to follow. Okay, so here we go. It can be a little tricky. I'm gonna just take it slow. You can remember how to do this because you're gonna run across it a lot. All right, first thing I'm gonna do is I'm going to square both sides, okay? So I'm gonna square both sides. You can do anything you want to any type of equation as long as you do it to both sides. So if I square both sides, I get r squared equals 25, okay? Now, I'm gonna replace r squared with the fact that we know r squared equals x squared plus y squared. Okay, so I'm just gonna replace r squared. Well, guess what I have now? I have a rectangular equation for a circle. Now, I don't know if you remember that the actual standard form for a circle, this is algebra 2 or college algebra coming up here, is x minus h squared plus y minus k squared equals r squared. That's the rectangular form for a circle, okay? So here's my circle. I don't have anything added or subtracted to the x and the y. That's because my center, which would normally be h and k, is at the origin. My radius, I take this other side and I take the square root because this is r squared. So if I take the square root, I get 5. And this is the same information that I came up with from the original polar equation. And I don't need to graph this because it's going to be the same graph, and I don't want it to actually look worse than it already does. So you can go back and forth between these rectangular equations and polar equations, and you know more than you think you do about the rectangular. And we're going to learn how to deal with what we know about the polar. So those are your types of circle equations. You have three types. You have the sine type, the 2a sine theta, y-axis symmetry. You have the 2a cosine theta, that's x-axis symmetry. And you have the r equals a number, which is going to be origin symmetry. Your center is here at the origin, and that number is your radius. And then this would be how you would go about changing it to a rectangular equation. Okay, so that was our first type. All right, second type. Here we go. This may be something that you're not familiar with. Okay, so I guess for all of you rednecks out there, you might say, oh, look, we have a lemicon. All right, you don't have a limacon or a lemicon. You have a limacon. All right, limacons. This is a soft S, limacons. All right, let's talk about what in the world is a limacon. Well, you have four types, and we're going to look at those down here. Okay, here are the forms. So it's still r equals, just like a circle, but now you're going to have a number added or subtracted to a coefficient sine theta or a coefficient cosine theta. So you have two terms here, one of them being one of these trig terms. That's how you know it's a limacon. Okay, now let's get into this a little deeper. All right, if we're using sine theta, then we're going to be symmetric to the x-axis, or in polar words, pi over 2. Okay, if it's a plus b sine theta, we're facing up. If it's a minus b sine theta, we're facing down. If we are dealing with the cosines and it's a plus, we're facing right, symmetric to the x-axis or the polar axis in polar terms. A minus b cosine theta, we're facing left. Okay, so that will kind of help us figure out what we're doing. So sine is up or down. Just look at your plus or minus to figure that out. Cosine is left or right. Look at your plus or minus to figure that out. Okay, now here are the four types of limacons. The first one, we have an inner loop inside. An inner loop is going to occur anytime a divided by b is less than 1. So for example, here's our example equation. This would be r equals this. Here's a, here's b. So if I take a divided by b, that's less than 1, I'm going to have an inner loop. Okay, now because of the plus and the sine theta, plus and sine theta, I'm also going to be facing up, and I'm going to be symmetric to the y-axis, or in other words, pi over 2. Okay, so what is that going to look like? That's going to look like a little inner loop that comes around a bigger loop, like that. That would be an example of an inner loop limacon. It's facing up, it's symmetric about this pi over 2, and there you go. Let's try that in our calculator. That's kind of fun. All right, we're going to clear out the r. We're going to put in 5 plus 7 sine theta, and we're going to graph. All right, now this one got very wide, didn't it? It's kind of crazy looking, but and you would have to zoom out almost a little bit, or at least increase your y max up a little bit more to see the whole thing. Now remember, the calculator wants to make things very wide. It's not supposed to be. It's supposed to still be more like what I have drawn, but you get the idea. There's a little inner loop here that happens, and it's pointing up. So that is what we call an inner loop limacon, that little inner loop there. Okay, let's look at the next one. Now I spelled this one horribly wrong. There does not need to be an extra I here. This is a cardioid, okay? A cardioid is going to almost look like an apple. It's gonna have a little dip. It's not gonna have an inner loop, but it is gonna have a little dip in it. This occurs when A and B are exactly the same, so that when you make a ratio of them, they reduce to 1, okay? Now, based on the plus and the cosine, our cardioid is going to face right, and it's going to be symmetric to the x-axis or the polar axis, okay? So what that's going to look like is you're going to have a little, there we go, okay? Almost like a little peach or a little apple that kind of dips in there, and it's pointing toward the right, just like that. And that would be an example of a cardioid. It does not have a loop, it just goes in at a very sharp point. So let's try graphing that. Okay, we're gonna clear this out. We're gonna put 5 plus 5 cosine theta, and we'll graph that. And there you go. That would be our cardioid, okay? All right, next one has no inner loop. So it's gonna look a lot like this, almost like a circle or a little egg a little bit. No inner loop. This occurs when that A-B ratio is greater than 1. Now I know this says equal to 1. It really shouldn't be. This is what happens when it's equal. But if it's greater than 1, that's what happens, okay? So if I take, here's my A, here's my B. So if I take 9 over 3, that is definitely greater than 1. That becomes a 3. Okay, so in that case, we're going to end up with, oh, there's our plus, there's our sign. We're going to be facing up, and we're going to be symmetric to the y-axis, or that theta is pi over 2. Okay, now this one is very difficult to differentiate between a circle. Okay, it's supposed to be just kind of like a little egg. So here we go. Okay, we're going to put in 9 plus 3 sine theta. All right, and there we go. Now the reason you know it's not a circle is because it is it's not symmetric around the center, and the center is not necessarily going to fall on an axis and be a complete circle there. So I guess mine really doesn't do it justice, but my pictures are usually pretty bad. There we go. Okay. All right, let's talk about a dimpled cardioid. So again, I have too many I's in there. So a cardioid goes in a sharp point. A dimpled cardioid just kind of dips in a tiny bit. It doesn't go quite as deep in that center there. This happens when your ratio of A over B is somewhere between 1 and 2. It's greater than 1, but it's less than 2, okay? Now, we're not worried about the sign. We don't want to do 7 over negative 5. We just want to do 7 over 5, okay? Don't worry about that sign there. Don't include the negative. Well, sure enough, that's going to be right between 1 and 2. The minus and the cosine mean we are facing left, and we are symmetric to the polar axis. Okay, facing left, and we are symmetric to the polar axis. Sorry about that, guys. There we are. Okay, so what we're looking at here is we're going to be facing left, all right? But instead of having a very sharp dip in, we're just going to kind of have a little, just a little dimple. It's not going to go all the way in sharp like this. It's just going to have a little bit of a dimple there. Let's look and see what that looks like on here. So if I clear that off and I put in 7 minus 5 cosine theta, and I graph it. There we go. And theirs, gosh, isn't even as pronounced as mine. I like mine a little more, but it just barely comes in. There's definitely a little dip there, kind of like a little bean, but it's not sharp like this one, okay? All right, so those are your limacons. Anytime you have sine theta or cosine theta and you have a number added or subtracted there in the front, that is a limason. Okay, now we're gonna go to my favorite, just because I think they're pretty. We have roses or rose curves. Some people call these flowers, all right? In this situation, we have sine and cosine again. We usually have a number in the front, but what makes these different is that we also have a number in front of theta. So that's how we know we're dealing with a rose or a rose curve, okay? Well, this coefficient tells us the length of each petal or leaf. The n, the number in front of theta, determines how many of those petals we have. If n is an odd number, that's how many petals we have. If n is even, we have to multiply it by 2. That's the number of petals we have. And to find the spacing of the petals, we just take 360 degrees divided by how many we have, and that gives us the spacing. So this is what we're looking at for our first example. All right, this is our A. Here is our N. Okay, so A equals 2. That is our petal length. Or boys, if you want to call it your leaf length, you can have a leaf. All right, then our N is 3. Now, that's an odd number, so I don't have to do anything to it at all. That's exactly how many petals I'm going to have. So I'm going to have 3 petals. Now, for my spacing of the petals, I'm going to take 360 degrees divided by 3, and each petal is going to be 120 degrees apart. Okay? All right, so let's draw our picture. And again, it doesn't have to be perfect because you're going to put it on the calculator anyway. All right, what we're looking at is something that's going to look like, there we go. There's your little rose curve, okay? Let's try to graph that on here. Clear this off. I'm going to put in 2 sine 3 theta. I hit graph. It's kind of hard to see there. What if I zoom in a little bit? There we go. How about that? So when I zoomed in, you were really able to see it. Theirs look a lot better than mine. Mine looks like some kind of balloon animal. But you get the idea. These petals are 2 units in length. There's 3 of them, and they're going to be spaced 120 degrees apart. There you go. All right, let's try this guy. Okay, here we have 3 cosine 2 theta. So in this case, there's our A. So we have a petal length of 3. So these petals are going to be a little longer. All right, here's our N, it's 2. Now that doesn't mean there's 2 petals. This is an even number. So to get my number of petals, I have to take 2 times N, which in this case is also 2. So I'm going to have 4 petals in this case, okay? And for my spacing, 360 degrees divided by 4, these petals are going to be 90 degrees apart. Okay, here we go. We're looking at 4, and they're a little longer. Okay, and there we go. That should be what our picture looks like. So let's try it. Let's go back and clear out this one. I'm going to put in 3 cosine 2 theta. Going to hit enter. Oh, I forgot to Let me put this on Zoom standard because I had zoomed in. Oh, I must have done something it didn't like. Let me go back. Well, it won't let me quit. It's just continuing to run. All right, hold on, guys. Here we go. What did I do wrong? 3 cosine 2 theta. Well, let's clear it out just in case. Is my mode still in polar and radian? So I'm good. Okay. 3 cosine 2 theta. And we'll graph it. I don't know why it was being weird before. Let's see if we can zoom in a little bit just to, oh, that's too big. Okay. All right, we'll go back to standard. There it is. Okay, that is our rows. Okay, that brings us to our very last page of shapes, and then we're going to actually get into the examples. So this is kind of a long one today. Okay, here we go. All right, so this is not a lemniscate, in case anyone's interested. This is a lemniscate, okay? A lemniscate. That's what we're looking at, lemniscates. Lemniscates look like infinity signs. They always have 2 petals, and there's always a petal length of A. So if you see R squared over here by itself, you have a lemniscate, okay? Lemniscate. Now you have me saying it. If you have R squared over here, it's a lemniscate. Then whatever this coefficient is in front of sine and cosine, take the square root, that is the petal length. If you have a sine, you have an infinity sign at a 45-degree angle, like this, in quadrants 1 and 3. If you have a cosine, you have an infinity sign that's horizontal right there on the x-axis. Okay, so here's our example. I didn't think we needed too many examples. All right, R squared, so I know I have a lemniscate. Okay, I'm going to take this number here, which is A squared. I'm going to take the square root of it. That is my petal length. I have 2 petals, so it's like an infinity sign. And because it's cosine, it's going to be horizontal right there on that polar axis or that x-axis. And there we go. Now, this guy can be difficult to put in the calculator because I don't have an R squared on the left-hand side under graph. All I have is an R. So I would have to take the square root of each side. So to put it in the calculator, I'm going to put in the square root of 9 cosine 2 theta, okay? This is how I'm going to have to put it in the calculator. So here we go. And I don't need the positive and the negative version. I just need this one. Big square root sign. I just hit second x squared, and that popped up. Then I'm going to put 9 cosine 2 theta. The whole thing is under there. And I'm going to hit graph. Now that's all it gives me. I don't know if you can see that there. That's all it gives me. You're going to have to use your imagination to fill in the rest. Because again, it's just an infinity sign. It's an infinity sign every single time. So there you go. We have a petal length of 3. It's horizontal, and you can fill in the rest. All right, and then I guess there is one more I forgot about down here, the little spiral of Archimedes. So that's an R equals a number times theta. So this is just an example. This is not necessarily exactly the form. The form is going to be R equals some number times theta. Now, if theta wasn't there, that's a circle. Okay, so we have some number times theta. And the spiral of Archimedes is exactly what it sounds like, a spiral. It starts at the origin, it spirals outward through each quadrant, and then it goes off into infinity. So if I were to put this in my calculator, if I put in 2 theta and graphed it, there it goes. And it's going to continue on forever to infinity. That is the spiral of Archimedes. Okay. All right, so now you know all of the general shapes associated with polar graphs. Here's like a little summary here. Okay. You have circles. They're kind of hard to read, which is why I went through and made you a little packet myself. Here are your lemniscates. Here's your 45 degree. Here's your horizontal. Here's your inner loop, lemmason, your cardioid, your dimpled cardioid. Here's your no inner loop. Here are your rose curves. Okay. It doesn't have the spiral of Archimedes on there, but it's just a spiral coming out of the origin. All right, let's jump right into examples then. So this is where your My Math Lab is going to start. Okay, example 1. Transform this polar equation to an equation with rectangular coordinates. Then identify and graph the equation. Okay, well, I can't graph him the way that he is because remember, when I go to graph, I have R's. This is in terms of R. So I'm going to have to change him from theta equals 11 pi over 6 to an XY situation. Then graph that and figure out what I'm looking at. Okay, so how do I do that? Well, remember, anytime we're dealing with theta and we're trying to determine a relationship between X and Y, we're going to use tan theta equals YX. Okay, well, I don't have a tan theta here. So what I'm going to do is I'm going to take the tangent of each side. So on the left, I'm going to have tan theta equals the right. I'm going to have tan of 11 pi over 6. Okay, well, what is the tangent of 11 pi over 6? We ought to be able to figure that out. Here we go. Put our unit circle on here. Here's 11 pi over 6. Here's cosine, here's sine. X, Y. We're going to put negative 1/2 over root of 3 over 2. Okay, so at 11 pi over 6, we're looking at the point root of 3 over 2, negative 1/2. So the tangent, 11 pi over 6, is Y over X. These 2's cancel. We get negative 1 over square root of 3. Okay, we're going to rationalize. Okay, and what do we end up with? Negative root of 3 over 3. That's what tangent of 11 pi over 6 equals. So I'm going to come back over here. I still have tan theta on the left, but tan of 11 pi over 6 is this value we found. Negative root of 3 over 3. Okay. All right. Now I'm going to continue using this equation, this tan theta equals y over x. So I'm going to replace tan theta on the left with y over x. Now I'm going to multiply both sides by x. So I'm going to multiply this by x and this by x. This is going to cancel. I get y equals negative root of 3 over 3 x. And there we go. Okay, so let's go through that again. I started out here. I took the tangent of both sides. It led me here. I then looked at the right side and I found the value for the tangent of 11 pi over 6. This was the point associated with it. I put y over x. I did some algebra. I rationalized. I came up with negative root of 3 over 3. I came back over here and I plugged that value in for 11 pi over 6, tangent 11 pi over 6. Then, because I knew that tangent of theta is y over x, I plugged that in. Then I multiplied both sides by x, or you could just shoot the x right over here, and this is what I ended up with. And it's an equation with no r's, no thetas, only a y and an x. So that is my equation. Now, what does this look like? Well, hopefully you remember what the equation y equals x looks like. Y equals x is just a line that goes through the first and third quadrant. Now, this is a negative with a coefficient, which means we're now switched over here. A line, it's supposed to go through the origin. It's a line through quads 2 and 4. That would be the graph you're looking for, and you're going to have 4 choices. Okay, what if you really had no idea that this is what that looked like? Okay, it's where your calculator comes in handy. But this is a rectangular equation, so you're going to have to go back to mode. You're going to have to go back to function. Now, you can leave it in radian, but you have to get it out of polar. Put it back in function. I go to y equals. I'm going to put in negative root of 3 divided by 3. Oh, I was supposed to do the whole thing, wasn't I? Sorry. Negative root of 3 divided by 3, the whole thing there, times x. Put this whole thing in parentheses. Now when I hit this button, an x pops up instead of theta because I'm in function mode. I graph that, and sure enough, that's exactly what we said it should look like. Okay? Exactly what we said it should look like. So that would be how you handle that problem. Let's try another one of those. Okay? Very, very similar. Let's see if we can follow the steps that we had. All right, we want to have rectangular coordinates, then we want to identify and graph the equation. All right, well, I have theta equals. When I have theta equals, I'm going to take the tan of both sides. Okay, so I'm going to have tan theta on the left, tan of 5 pi over 4 on the right. Now, I know that tan theta is y over x. Remember that little formula that we had? I just love to get this thing all out of focus, don't I? Okay. What is tan of 5 pi over 4? Well, we have to go to our unit circle. Here's 5 pi over 4. Here's x, here's y. Cosine, sine. Okay, so if they're exactly the same number, they're both negative. So when I put one over the other, I'm going to get a positive. If I put negative root of 2 over 2 divided by negative root of 2 over 2, I'm going to get 1, a positive 1. So that came right off our unit circle. Okay. So if I put 1 over the other, I'm going to get a positive 1. If I multiply both sides by x, or if I just shoot them over, however you'd rather do, I get y equals 1 times x, or just x. And there it is. That's that little rock star equation that takes us through a line through quads 1 and 3. And there we go. Okay. If you weren't sure about that, remember, put yourself back in function mode. Y equals. Okay. All I'm going to do is hit X. And there it is. There's my graph. And that's the one that I would click on. Okay. So we have been looking at this guy over and over and over again. Anytime we see a theta, that's how we change him into y and x. All right, well, if you recall, we had 2 others. We had x equals our cosine theta, and we had y equals r sine theta. All right, well, let's look at example 3. We want to do the same thing here. We want to take it to a rectangular equation, and we want to identify the graph, and we want to graph it. All right, well, we have r sine theta equals 5. Well, we just said, what does r sine theta equal? Y. So, because y equals r sine theta, I'm just going to substitute that for y. There's our equation. And what does y equals 5 look like? That's a horizontal line. There you go. You identified it and you graphed it. Perfect. Okay, along those same lines, what about example number 4? We have r cosine theta equals -4. What is r cosine theta equal to? X. There we go. We do that one little substitution. What does that look like? Oh gosh, that's not a vertical line, but pretend it is. That's supposed to be a nice little vertical line at x equals -4. All right, easy enough. Okay, let's try the next page. Okay, here we go. All right, example number 5. Okay, transform the polar equation to an equation with rectangular coordinates, then identify and graph the equation. All right, well, I already have an r equals over here, so I could throw this right into my calculator in polar form and immediately identify my graph. If you go back to those examples at the beginning of the packet and you're looking for something that looks like this is actually a circle. That's actually a circle. Okay, so if you recall, we said that the standard form of a circle in rectangular form looks like this, okay? Where your center is HK. All right, so let's see if we can turn this polar equation into something that looks like that. All right, first step, we are going to multiply both sides by r, because I need an r squared right here. Now, why didn't we just square both sides? Because I also need an r over here. I want this to say r cosine theta, so I can replace it with an x. Right now, it's just cosine theta. And if I square both sides, then I'm going to have cosine squared theta, which is still not helpful. So I'm going to multiply both sides by r. I'll just slide that little r right in there. Now we know that r cosine theta is x. We also know, what is r squared equal to? X squared plus y squared. Look at there. All right, I'm getting myself a rectangular equation. Now, it's still not in this form, still not in the form we want for a circle, but at least I don't have any r's and thetas hanging around. Okay, so I replaced this with x squared plus y squared. I had multiplied both sides by r, so now this is an x, okay? I'm going to move all those terms to the left, and I'm going to sit them next to each other. So I'm going to have x squared plus 6x. Now, in order to get it into this form, you have to think way back to college algebra. We have to complete the square. So if I'm going to complete the square, I'm going to leave room for that little constant that's going to help me do that. Now, I still have plus y squared. I don't have to complete the square for him because I don't have a y term. I just have y squared. Equals, and then on this side I'm going to have 0 plus another blank, right? Because if I put a blank here, I have to put a blank there. Okay, so now I'm going to complete the square. And I only have to do it for x because I don't have a y term. All right, now, Anybody remember what we put in these blanks when we complete a square? We put in b divided by 2 squared. That's what's going to go in each of those blanks. This is my b. So I'm going to have 6 divided by 2 squared. Okay, so 6 divided by 2 is 3. 3 squared is a 9. That's what's going in both of those blanks over there is a 9. So I'm going to put that in there. Now I'm going to make my parenthesis packet. Square root of this term, sine of the middle, square root of the last term, plus y squared, equals, clean up the right, 9. This is my equation. Okay, so I moved 6x over and I set it next to his x term and I added a blank. There's my y squared. He doesn't get a blank because he doesn't have a y term. I also added a blank to the other side because whatever I do to this, I have to do to that. Then I use this little formula, b over 2 squared, to find what goes in the blanks. Then I have a parenthesis with a square. Square root of the first term is x. Sine of the middle term is plus. Square root of the last term is 3. And then I finish the rest. Okay, what does this tell me based on my standard form of a circle? It tells me that my center, okay, remember it's the opposite sign of what you see in the parentheses, is -3, and I don't have anything here, 0. Tells me my radius, square root of this, 3. And now I know I'm looking for a circle whose center is at -3, 0, and whose radius is 3. And there's my circle. So you can identify it. So that algebra part about completing the square, that's going to come back to haunt you a few times. You want to make sure you're comfortable doing that. Okay, now you could have also gotten that information from up here. A cosine means that you're symmetric about the x-axis. If you pull out a 2, then you're left with an A of -3. That's your center. Your radius always has to be positive because it's a distance. So you take that -3 and you make it positive, and there it is. Okay, but you will have to be able to write this equation. All right, let's try it with this one. Okay, we want to do the same thing. Now this one seems a little bit harder because I don't see sine or cosine here. I don't see either one. And I definitely don't have an r situation where it's r equals either. Okay, well, we know that cosecant of theta is really 1 over sine theta. So let's rewrite this. We're going to have r times 1 over sine theta equals 2. Now let's multiply both sides by sine theta, or you can just shoot that right over there, however you want to do it. That's going to give you r equals 2 sine theta. There you go. That's a circle. That's a circle that is symmetric about the y-axis with a radius of 1 and a center at 0, 1. You can put it right into your calculator in polar form to look at it, but we want an equation with rectangular coordinates. Okay, so you can find that information and plug it right into this equation, or you can complete the square and solve it that way. Okay, let's practice. So I'm going to multiply both sides by r. When I do that, I get r squared equals 2r sine theta. Now I can make 2 substitutions. On the left side, I'm going to have x squared plus y squared. On the right side, I'm going to have 2y. So I multiplied both sides by r. Now I'm substituting. Now I'm going to move all the terms to the left. going to subtract the 2y over there, and I'm going to add a blank. Okay, because I'm going to complete the square. I don't have any x terms, so he's just there. The minus 2y, to get him over here, he's going to sit by y squared, and I'm going to add a blank because I'm going to complete the square. So I have to add a blank over here as well. All right, what's going to go in my blank? I'm going to have b, which is -2, divided by 2 squared. This would be -1 squared is +1. That's what goes in my blank. Okay, x squared plus, now I'm going to have parentheses squared. I'm going to have square root of the first term, sine of the second term, square root of the last term, equals what's over here on the right. That's my rectangular equation. From this information, I know I have a center at 0, +1, because remember, it's the opposite signs. And a radius, square root of 1, which is 1. When I graph that, I'm looking at that. Okay. So there we go. You could have gotten that information right here at this point. And then you could have used that information to just plug into this equation and gone about it that way if you wanted. So either way that you want to do it, but as long as you're able to complete those 3 parts, okay? Equation, discuss the shape, pick out the graph. All right. Example 7, let's move on to some other types. Okay, for 7 and 8, I notice they're very similar. I have a constant minus a coefficient and a trig term. Anytime I see that, I know I'm talking about a limacon. Now, they may be different types of limacons depending on the ratio of A and B, but I know they're both limacons, okay? And this guy resembles this form for a limacon, which means that whatever I find is going to be facing down because of the minus, and it's going to be symmetric to the x-axis, or theta equals pi/2, and that's from the sine portion. Okay, let's check out A and B. So they both happen to be 9s. Remember, we don't take that sign into account. We just take the values. That equals a 1 when I do the ratio. Okay? Anytime we have a 1, I have a cardioid. Okay? So here we go. We're going to have a cardioid that's facing down, that's symmetric to pi/2. And there we go. Now, 7 and 8, I didn't have to change this to a rectangular equation. All I had to do was identify it and graph it. So I identified it and I graphed it. And so on my math lab, there'll be 4 choices and you just pick. Okay, so if I'm not really good at identifying these, what can I do? Well, I can go to mode, radian, polar. Then I can go to y equals, which is now r equals, 9 minus 9 sine theta. And lo and behold, I can pick out the graph. Well, no matter how I zoom, I can't get it just perfect, but I can pick out the graph that looks like a cardioid. Okay, there we go. All right, let's look at example 8. All right, still a limacon. This one is of the form a minus b cosine theta. Still facing down because of that minus, but the cosine means I'm symmetric to the polar axis, or the x-axis. Okay, now let's look at my A and B ratio. I'm looking at 20 divided by 10, which is 2. This means it's greater than 1. So this is no inner loop, okay? No inner loop, and it's facing down. So I'm looking at something like that with no inner loop. Okay, so let's go back here if I need to and plot it. I'm going to do 20 minus 10 cosine theta. Oh my goodness, that is gigantic. Okay, let's zoom out, and there it is. Okay, no inner loop, there it is. Okay, and you can identify it from there. All right, we've got 12 of these total, so we're moving right along. We don't have to convert these to rectangular. We simply have to identify and graph. That's it. All right, when I take a peek at number 9, at first it may look like it's a circle, but this number in front of theta means that you are looking at a rose. Okay, we have an N. So remember, in this case, I'm looking at a cosine in theta. All right, this tells me, which is A, I have a petal length of 7. Okay, my N is 2. Okay, N equals 2, which is even, which means that my number of petals is going to have to be 2 times N. I'm going to have 4 petals. And if I'm looking at my spacing, I'm looking at 90 degrees apart for that spacing. All right, here we go. So I want to identify the graph that looks like that. Now, I can always go in, I can graph it, 7 cosine 2 theta. Let's do a standard here. There we go. That's what I'm looking for. And I would just click on the graph that looks like this, that has this information. Okay, this is what it means by identify. This is what it means by graph. Just pick the graph. All right, I have another rose because I have a number here in front of theta. Okay, this one, here's my A. I'm going to have a petal length equal to 2. Here's my N. N is 5. Since that's odd, I'm going to have 5 petals. Okay, I don't have to multiply it by 2. If it's even, you have to multiply N by 2. Okay, for my spacing, I'm going to have 360 degrees divided by 5. That gives me 72 degrees apart. Okay, so that's kind of hard to do here to figure it out, but basically what you're looking at is a little flower that looks like that. That is not spaced out well at all, but you know, I do the best I can. Okay, let's clear this out. Okay, and put in 2 sine 5 theta. Okay, oh, there he went. All right, so look at that. That's kind of neat. All right, so that's really what you're looking for, spaced out better than this one. But there you go. All right, number 11. I see an r squared situation. If you see r squared, you're looking at a lemniscate. Okay, we're looking at a lemniscate, so that's the infinity sign. The cosine means that I'm going to have a horizontal infinity sign. We always have 2 petals because it's the infinity sign, right? So 2 petals. Now I just need to know how long are they? Well, this guy is a squared. So if I take square root of 81, that tells me that I have a length of 9. Okay, that's my petal length. All right, those are long petals. Okay, so That's basically what I'm looking for. Okay, let's see if we can graph that. I'm going to put in, remember, this is the one I have to do the square root because of r squared. 81 cosine 2 theta, graph him. Oh, I forgot to zoom out. Sorry guys, let's do that. Zoom standard. All right, then you'll just have to use your imagination that the rest of these close into a nice little infinity sign right on the horizontal axis. All right, last but not least, example 12. Okay, identify and graph the polar equation. All right, well, anytime I have r equals a number theta, I'm looking at the spiral of Archimedes. Okay, and he's just going to spiral outward. There you go. That's what you're looking for. Now, let's just test him to make sure. I'm going to put 7/8 in parentheses, and then I'm going to hit theta, graph. There we go. There's our spiral. Okay, we are done with 9.2. I hope you didn't find it too intimidating. It's kind of fun. Once you learn to use your calculator, make sure that you're in polar mode, you're in radian mode. And then if you do want to go back and check those rectangular graphs, don't forget to switch back to function mode. That'll get your x variable back for your graph. All right, text me, call me, email me, whatever you need with any questions you might have. And I will talk to you in section 9.3. Bye-bye.